Everyone says CoWoS capacity isn't enough. NVIDIA's chips can't get out because they are stuck at CoWoS. But if you only know about CoWoS, then you might only understand half the situation. Because inside TSMC's arsenal, there is another weapon more advanced and expensive than CoWoS. And it is the secret weapon that can truly extend the life of Moore's Law. That is SoIC. In today's video, we are not only going to talk about what SoIC is, but also dismantle the most complicated classifications within this technology for everyone. TSMC has now split SoIC into the X series and P series. What is the strategic significance behind this? And what is the difference between the SoIC-W and SoIC-C we often hear about? More importantly, in this 3D packaging war, it's not just TSMC playing. Intel has Foveros. Samsung has X-Cube. Who will be the final winner? Today we will explain it all clearly at once. We have to clarify a concept first. Why do we still need SoIC when we have CoWoS? What is the difference between the two? Simply put, it's the difference in building houses. CoWoS, which is what we often call 2.5D packaging. Its concept is more like building a row of townhouses or villas. We place logic computing chips, like GPUs, and memory chips, like HBM, side by side, on a very large silicon interposer. They are neighbors, living next door, although the distance is already very close, and there are many interconnecting circuits in between. They are ultimately still two separate houses. But SoIC is different. It is true. 3D packaging. The concept is building a skyscraper. We no longer let chips live next door, but directly place one chip, stacked on top of another chip's head. The benefit of this is very obvious. Because of vertical stacking, the signal transmission distance is the shortest, resistance is the smallest, and speed naturally becomes the fastest. So you can imagine SoIC as the internal martial arts Nigong of the processor. It is responsible for stacking computing units to become a super brain, and CoWoS is the external martial arts Weigong. It is responsible for connecting this super brain with the adjacent memory. So the two do not replace each other, but are in a cooperative relationship. Currently, the top-tier AI chips usually finish SoIC first, and then go to do CoWoS. Speaking of this, you might ask, since 3D stacking is so powerful, could it be that only TSMC knows how to do it? Of course not. This is actually a battleground for the global semiconductor Big Three. Intel actually laid out plans in this area very early. They have a technology called Foveros. If you recall Intel's previous Lakefield processors, or the newest Meteor Lake, they all heavily used this 3D stacking technology. Intel's strength lies in realizing very early on that chips should be split apart to be made, and then stacked back together. So their integration capability on the design side is very strong. The other one is Samsung. Their technology is called X-Cube. Samsung's advantage lies in being the memory leader, so in stacking SRAM or HBM. They are very aggressive in related technologies. However, why are the most successful products seen on the market now, like AMD's Mi300 or Apple's chips, mostly still choosing TSMC? This involves the key point we want to talk about today: technical precision and yield rate. This brings us to TSMC SoIC's two secret weapons, SoIC-X and SoIC-P. People might not know. Early SoIC actually referred to what is now SoIC-X. Later, the P series was separated for market segmentation. Let's talk about SoIC-X first. This X stands for extreme, meaning extreme performance. It uses a very black technology, advanced tech, called hybrid bonding. What does this mean? In traditional chip packaging, no matter how closely you stack them, in the middle, you usually rely on small solder balls. We call them bumps or microbumps to conduct electricity and connect. This is like stacking to bricks and applying a layer of cement in between. But as long as there is cement, there is thickness, there is resistance, and the signal will have latency. The most insane part of SoIC-X's hybrid bonding is that it has no bumps. It grinds the two chips directly to be very, very flat to the atomic level, then allows the copper wires above and the copper wires below to directly fuse together under high temperature and high pressure. This is like cold welding. The two pieces of metal grow directly together. There is no solder in between, no gaps. The connection density created this way is extremely high. The pitch can be reduced to below 9 microns, and even moving towards 3 microns. This is currently the method that can achieve the fastest signal transmission in physics, like AMD's AI chips or Apple's high-end chips, which pursue performance regardless of cost. They use this SoIC-X. But SoIC-X has a fatal drawback: it's too expensive, and the manufacturing difficulty is extremely high. Think about it, aligning to chips to the micron level without any dust. Controlling this yield is very difficult. So, in order to make 3D packaging technology accessible, and not just for the top billionaires, TSMC launched SoIC-P. This P stands for pervasive, meaning universal, or you can understand it as performance or cost, which is price-performance ratio. SoIC-P doesn't go the route of extreme bumpless technology. It goes back to using the microbump technology we are familiar with. That is to say, when stacking, there are still tiny solder balls connected in between. You might think, isn't this going backward? Actually not. SoIC-P's microbumps are much denser than the bumps in traditional packaging, roughly between 18 to 25 microns. Although it loses to SoIC-X's bumpless technology, its advantage is a significant reduction in cost. The process is also more mature, and yield is better controlled. This is for things like mobile chips and automotive electronics, which are sensitive to cost, but still want some benefits of 3D stacking. It is very attractive. So, TSMC's move is very brilliant, using X to conquer the top-tier AI market, and using P to take down the future mobile and consumer electronics market. This is a strategy to eat up both high and low ends. After understanding how X and P are connected, finally, we want to talk about how they are stacked. This is the SoIC-W and SoIC-C that everyone often hears about. The difference between these two words lies in that W and C. W is wafer, C is chip. SoIC-W is wafer on wafer, stacking wafer on wafer. This method sounds very bold. Take a finished 12-inch wafer and stack it directly on another 12-inch wafer, and then cut them open all at once. Doing this maximizes production capacity. Alignment is done in one go. However, it has a huge risk. Everyone knows that when a wafer is made, it's impossible for every single chip on it to be good. There will always be some broken, defective products. If you stack one wafer on top of another, and suppose you stack a good chip on top of a bad chip, then this stack is scrapped. Conversely, stacking a bad one on a good one is also scrap. This will cause the yield to slide down like a slide. This is the so-called known good die problem. So, SoIC-W is usually only suitable for products with extremely high yields, or very repetitive and simple structures, like memory. Therefore, the mainstream for logic chips currently is actually SoIC-C. That is chip on wafer, stacking chips on a wafer. This method is much smarter. We cut the wafer open first, pick out the good chips that passed testing, and then place them, one by one, precisely onto another complete wafer. Although this method is more labor-intensive, picking one by one, it ensures that every chip we stack is good, and won't waste the wafer underneath. Moreover, SoIC-C has a huge advantage, which is heterogeneous integration. You can take a 3nm CPU, and stack a 5nm cache memory on top of it, or even stack sensors with different functions. This ability to mix and match like Lego bricks is the true essence of the chiplet era. The most famous example is AMD's X3D series processors. If you play games, you must know that there is a version of AMD's CPU with a huge L3 cache that actually uses SoIC technology to forcefully stack another layer of SRAM chip on the original CPU chip, building memory directly upstairs from the computing unit, making data retrieval speed incredibly fast. If you like this kind of hardcore technical analysis, don't forget to subscribe to our channel. See you next time.